Alright, today we're going to be going over problem number 5 of homework 2. Now, problem number 5 basically gives us this equation right here for a density function, which is basically the quadratic with this constant a that we are not aware of. It also gives us that we are working in a range where x is between negative 1 and 1. Otherwise, everything outside that range is 0. So it makes things a little easier. First and foremost, this equation is broken up into A and B parts. We're going to start with part A, which is basically solving in order to get the constant A. Now, the way we do that, the logic is that basically if this equation is truly a density function, okay, then we should be able to actually, by taking the integral of it from negative infinity to positive infinity in order to get the distribution function, this whole term should equal 0 by definition. Alright? Now, we're going to use this equation and solve it for A in order to get a constant for A for this part. Now, the other thing we should see is that the only region which actually has area under the curve, given this criteria right here, is the region between negative, where x is between negative 1 and 1. Thus, this equation can actually be reduced down. So instead of negative infinity to positive infinity, we can work from negative 1 to positive 1. So let's work it out. As I mentioned, reduces down. We bring down our f of x. We bring out the constant a. We don't have to work there. So now we have the quadratic within the integral form from negative 1 to 1. We use the formula accordingly for this integral, which is x to the third over 3, common. Top term, 1 to the third over 3 is 1/3. This substitute in is negative 1/3. 1/3 minus negative 1/3 or plus 1/3 is equal to 2/3, which as we defined is equal to 1. Thus, our conclusion is that A is equal to 3 over 2. Thus ends part A of our problem. Now, for the fun part. Part B of our equation basically defines a region M, whereby we're working not between negative 1 and 1 like up here. We're specifically working from negative 1 to negative 0.5, excluding the region between negative 0.5 and 5, and then working in the region between 0.5 and 1 on the x-axis. Alright? So the question is that they want us to redefine our density equation given that we are specifically working within this M region. This condition is, we have to make sure that this condition is met. So, how do I mean by redefine? We have to make sure that this density function, working only within this range, when we take the integral over the entire thing, is going to be equal to 1. Alright, so how do we do that? Well, I wrote a little bit out here. A lot of it I just mentioned is that we can define 2 points to break the actual negative 1 to 1 region up. We define the negative 0.5 and 5 point on the x-axis. Let's see here. We define the region between these 2 points to be 0. Alright. Obviously, because we're working in a quadratic, we know that we have symmetry around the actual x-axis. So technically what we could do is look at our work to the left of, we have symmetry around the y-axis, pardon me. And we can look at our work to the left of the y-axis, and that's probably going to have a symmetrical equivalent to the right of the y-axis, which is good. Now, let's see if I forgot anything here. No, that's about it. The one other thing is that when we actually work this out, if we actually take the area of this to the left, to the whatever curve we create, we need a curve that to the left of the y-axis, the area under the curve is going to be equal to 0.5, and then to the right of the y-axis, the area under the curve is going to be equal to 0.5. Thus, the total area will be equal to 1, which we need in order to meet the criteria for this being a density function, even in this space. So, let's play that out. we have these equations which are given to us, but the one difference is that we have to multiply the whole thing by 1/2 to actually define this. I'm just working within this part, within this region to the left of the y-axis. Later on, I work to the right, but they're going to be symmetrical, so whatever I do here, probably going to have the same equation on the right. So, I define it this way. Basically, the region from -1 to -0.5 is defined as our density function divided by our distribution function right here at A. Alright, so what we work that out to be is we take original calculated f of x with the actual constant substituted in, we integrate it from -1 to -0.5, we solve it in, and we get this right here, which is basically equal to 7/16. Thus, if we substitute in the constants that we know here, down here, okay, we have our original 3/2x squared. We divide by this f of a, 7/16. We just multiply here 16/17, same thing. We multiply the whole thing by 1/2. And what that works out to be is 12/7 times x squared for within this region. And the region from -5 to 0 remains 0. Now, I'll go through the actual work in a moment. The idea is that to the right of the y-axis, like I said, because we have symmetry, because we have working with a quadratic equation, we should get the same equation. But we'll work it out as a check. So, working on the right side, we develop these equations right here. Notice the 0 from 0 to 0.5. Based on the equations offered to us, we have this. We, again, multiply times 1/2. We find f of b, which is basically defined from all the way on the left, which is -1, all the way to 0.5. We integrate. We get the sum, which is equal to 9/16. We substitute all the constants in here. Okay, here's our original f of x over 1/2, then 1 minus this term. And we again get the same term we had earlier, 12/7 times x squared, which we had right there. So we have a check. So the ultimate answer to our new density function under the condition that it exists within the actual M space is that we have it defined as 12/7 x squared from -1 to -0.5. 0 in this region between -5 and 0.5, -0.5 and 0.5, and 12/7 times x squared between 0.5 and 1. Now, if we draw that out, notice how real lightly we actually drew out the original f of x equation, this quadratic, which corresponded to the 3/2x squared. Notice how things have changed. Curve has gotten steeper and is only defined between the 0.5 and 1 and the -1 and 0.5. So this is the equation within the M space. You have this curve, stops abruptly at -0.5, is 0 up to 0.5, then picks up again. Notice the symmetry, though, between whether we're working with f of x or f of x on the condition of M. And that's the end of our problem.